This lecture is about the average kinetic energy per molecule of a gas. This is the specific equation that helps us calculate the average kinetic energy for every molecule in a gas. I'll have a separate lecture where I explain where this equation comes from, but the high school IB physics course does not expect you to be able to prove the equation. So for this lecture, I'll just take it as a given. I can see that the average kinetic energy is equal to 3/2 times Kb, which stands for the Boltzmann constant. It's a specific constant, multiplied by the temperature, and it's also equal to 3/2 times the ideal gas constant over Avogadro's number, again multiplied by the temperature. I can see that this implies that this new number, Boltzmann's constant, is equal to the ideal gas constant over Avogadro's number. I'll show you how to use this equation in a minute. I just need to clarify some of the variables. So the average kinetic energy is not the total kinetic energy in the gas, it's the total kinetic energy divided by the number of particles. So it's literally the average kinetic energy per particle. As an example, if we take this box on the right, I can see I have a particle with 5 joules, 1 joule, 8 joules, and 6 joules. So the total kinetic energy is 20 joules, but there are 4 particles, so that means that the average is the total kinetic over the number of particles, which is equal to 5 joules per particle. So that would be the average kinetic energy per particle in that gas. That's what that variable is referring to. Because this is an ideal gas, all the energy is kinetic, so the total kinetic energy is the total internal energy in the gas. Sometimes IB questions ask you to calculate the total internal energy in an ideal gas, and they always mean the total kinetic energy, because in an ideal gas, all the energy exists as kinetic energy. This equation can be a bridge between the ideal gas law and the average kinetic energy equation. If you're given the total internal energy of the material, you can connect the equations using this pattern. So if I have PV equals nRT, I can use that to find N, and I can use N to find the number of particles in the gas, and I can use the number of particles in the gas along with the total internal energy to calculate the average kinetic energy and set that equal to 3/2 times Boltzmann's constant times the temperature. So you can go from one to the other if you have the total internal energy of the gas. We can use the kinetic energy equation along with the average kinetic energy equation to find the average velocity of particles in a material. Because kinetic energy is 1/2 mv squared, the average kinetic energy is going to be 1/2 times the mass of any one particle times the average velocity of all the particles squared. Remember that we assume in an ideal gas that all particles have the same mass, so we could say the average mass of all the particles, but we're assuming that all the masses are the same, so that's just the mass of any one particle. As an example, the temperature of argon gas is 330 Kelvin. What is the average velocity of each particle of the gas? So I know the temperature is 330 Kelvin. This is Boltzmann's constant. And the mass of a particle is equal to the material's molar mass divided by Avogadro's constant. That's the mass of one individual particle of a material. I can see that the molar mass of argon is about 40. It's at the bottom of its symbol on the periodic table. So that means that the molar mass is 40 grams per mole, and I put that over Avogadro's constant to get this mass of any one particle of argon. And I want to convert this to kilograms because that's the mass that we use in the kinetic energy equation. So I divide that by 1,000 and get 6.6 times 10 to the negative 26th kilograms. This is the equation for the average velocity. I just rearranged the average kinetic energy equation. And when I plug in my other equation for kinetic energy, 3/2 times Boltzmann's constant times temperature, this is what I get. Plugging in the numbers that I'm given, I get a final answer of 455 meters per second. So that would be the average velocity of any one of the particles in the gas. This equation only works for an ideal gas because, again, there is a linear relationship between the total kinetic energy and the temperature. You can see using y equals mx that fits that same linear form. So this equation also only works when we're dealing with ideal gases. Using the equation on its own is pretty simple. I'll finish with 2 example problems. In example 1, the average kinetic energy of a gas is 9.32 times 10 to the negative 20th joules. What is the temperature of the gas in degrees Celsius? So I have the average kinetic energy. I'm always given Boltzmann's constant. This is also in your IB packet. So plugging these into my equation and rearranging to find the temperature gets me 4,500 Kelvin. And because this is asking for degrees Celsius, I need to subtract 273 degrees. So this is actually equal to 4,227 degrees Celsius. In example 2, helium gas is contained in a volume of 3.5 times 10 to the negative 4th meters cubed at a temperature of 300 Kelvin and pressure 5 times 10 to the 5th Pascal. Calculate in joules the internal energy of the helium. So this is the volume, and this is the temperature, and this is the pressure. Boltzmann's constant. And we use this notation for the number of particles, capital N. And I know that lowercase n, the number of moles, is equal to the number of particles over Avogadro's constant. And this is Avogadro's constant. And this is the ideal gas constant. So I'm just writing down everything I know because this is actually going to require me to use both the ideal gas law and the average kinetic energy formula. So the total internal energy is equal to the average kinetic energy multiplied by the number of particles. And I know that the number of particles is equal to the number of moles multiplied by Avogadro's constant. So I'll replace that in my equation. And the average kinetic energy is equal to 3/2 times Boltzmann's constant times temperature. And rearranging PV equals nRT for N gets me this. And so when I plug all these in, I'll be able to get an equation with only the variables that I already know. So this is a lot, but I know the value of every single one of these variables, so I can plug in those values, and when I do that, I get a final answer of 262 joules, so that's the total internal energy of the helium. And that's how you use the average kinetic energy per molecule equation to solve problems.